Right, today I will talk about the implementation conditions and the parameters. As a review, I want to talk about why the implementations are necessary. First of all, the implementations requires to address several problems in the Big Bang theory. Uh, the one among sort of that one is the horizon problem. The horizon problem is the cause there is some from the CMB we know that the temperatures in the different points correlate each other. But if there's no implications as a standard Big Bang theory, then such a correlated temperatures cannot be explained. First of all, let's define the what's the horizon size of the cosmic expanding universe. The a typical expanding universe matrix given like that with the scaling factors A, and we will define the conformal time to make the temporal part and the spatial part is inserted in the same terms. Then the conformal time tau is defined by the dt through the A. Then the horizons is can be obtained by the integrations of the d tau. So there are some of the changes of the variable dt of the a and the a dot and the Hubble parameters given by the a dot over the a. So the horizon size of the tau is given by the integrations of the 1 over the ah is over the dl and I. And if we calculate the for some of the given solutions of the scaling factors like as radiation dominance, the matter dominance, or the cosmos constant dominance as a functions of the time, then the horizon size is actually the proportion to the 1 over the AH is with the addition as a coefficient. We call this 1 over the AH is a Hubble horizon or Hubble radius. And the 1 over the AH is actually same with the 1 over the A dot. And if we insert the solutions of the scaling factors for each type, a to the a is a proportional t to the n, and n is smaller than the 1. Then when the universe is radiation or matter dominance, then the Hubble horizon size becomes the largest along the time. But in the cosmological constant dominance, the A is proportional to the exponential ATT. So the Hubble horizon size becomes decreasing behaviors along the cosmic history. So keep this box. Last reviews on the horizon problem. This is the space-time diagram with the conformal time with the y-axis, and the light cone has a 45 degree in such a conformal diagram, and this is the presence time, and at the CMB is the photon should be correlated, but if we consider the radiation dominance torsi here, then the light cone at this point and at this point is causally disconnected. So to explain such a correlated CMB, we it demands the causally connected light cone, and if there is implantation, then there can be the time pulse causally connected here. So to explain such a horizon problem, we can have the implementations time. So this is the evolution of the Hubble radius on about the A axis over the L and I. There are three different periods in the cosmic history. First one is the implantation. During the implantations, the Hubble radius becomes decreased, and during the radiation and the matter dominance, the Hubble horizons increased, and actually the when the the transition from the early to empty, the slope becomes changes. And in the late universe, the dark energy dominance, with accelerated expansions, then the Hubble radius becomes decreasing behavior. But we'll ignore the such lambda d here, and the um, CMB appears at this time. But if we consider the Hubble origin size, at the radiation's dominance, the Hubble origin size becomes smaller than the 1/AH is at the CMB. So there was a problem. So to make the causally connected with the relatively large Hubble origin size in the red universe, it requires implications. And we can derive the implantation conditions to make the causally connected temperature. So during the distance at here, the presence time 1/A0 to H0, and we will compare the Hubble origin size at the rating RH. Here's a right here's comparison. And then we will use the some several bar. First of all, during the radiation, the A is proportional to the 1/2. As if we evaluate the Hubble parameters, then the Hubble parameter h is proportional to the 8 to the minus 2, so that this right here becomes this one. And the rating temperatures, we adopt some typical value 10 to the 15 CV. This value is related with the before the barrage analysis. And the universe temperatures during the current time the 10 to the minus 3 electron volts. So this right here is given by the 10 to the 28. And during the impulations, the evolutions of the Hubble horizons, during this time, the Hubble parameters are almost constant. So that is right here just given by the right here scalar inductance, and this right here should be larger than the 10 to the 28. And if we calculate this once again with the logarithm, then the answer of the rating temperature and implantation should be the larger than the 60. So it is called the 60 E-port implantation conditions, and we will return these conditions again. Now I'll turn to the condition for the implantations. The first of all, the implantation requires accelerated expansion, so the 2,000 of the A should be larger than the 0. And already we saw that the Hubble radius should be shrinking, so that these conditions are written like that. And if we calculate these conditions, then the derivatives yield that the 2,000 of the A should be larger than the 0. So the condition 1 and the condition 2 is equivalent. And if we calculate the condition 2 with other way, then we can parameterize by the epsilon as the minus of the Hubble dot over the Hubble scale, and by using the shrinking Hubble radius, the epsilon should be the smaller than the 1. So it means that the Hubble parameter should be the slow varying behavior. So this epsilon is actually the dimension of the 1, because the Hubble scale is 1 over the t scales, and Hubble dot is 1 over the t dot times 1 over the t. And there are also the additional equivalent condition by using the Brodmann equation, first Brodmann equation, continuity equation, and second Brodmann equation. Among that, only the two are independent in here, and the second Brodmann equations can be obtained at this process. Hubble dot and Hubble scales actually becomes a to the third over the a. And if we insert the first Brodmann equation into the second Brodmann equation, then we can obtain the continuity equation. And if we manipulate the sum term, then the result becomes epsilon as minus the Hubble dot over the Hubble scale, and the epsilon should be the smaller than the 1. And the result of the epsilons given by the functions of the pressure P and energy low. Then we can check the equation of the state omega should be smaller than the minus 1/3. So those conditions actually is the same with the negative pressure, which is the breaking of the strong energy conditions. So to be specific, I will explain some more condition for the impulations. The epsilon sum minus over the subscales can be changes to these terms as changes of the whole parameters over the n-fold impulsion as n is defined as the ln and actually this is the same with the HDT. There are some of the calculations process here. So the point is the slow varying parameter epsilon, which parameterizes the changes of the Hubble parameters over the unit, some of the unit quantity, and the epsilon should be the smaller than the one. It means that the Hubble parameters are almost constant during the impulations with the slow varying behavior. And also we want to make the epsilon is also the small in the long time. So the change of the epsilon should be the small, and this can be parameterized by the eta, which is defined as a changes of the ln e over the unit quantity. And if we calculate this one again, then the eta becomes epsilon dot over the h epsilon. Also the dimensions of eta equal to the 1, epsilon dot 1 over the t, and the h is 1 over the t. And eta should be the smaller than the 1. So that there are two conditions: epsilon should be the smaller than the 1, and eta is just the smaller than the 1. And the small epsilon meaning that the Hubble is almost a constant, and the small eta means that the small epsilons maintains in the long time. So now let's realize some of the specific impulsion model. For simplicity, we will use a scalar field, and there's some here a brief review of the scalar field expanding universe. The action is given like that already. We discussed it in the previous video. There's elements that contains the matrix, and if we calculate the stress analysis tensor by using the classical field theory, then we can obtain the annedancy and the projects as a functions of the pi dot and the pi. And if we calculate the equation of the motion by using the actions, then we can obtain this formula to the pi with the Hubble prediction term. And if the Hubble prediction term is the roughly the same order with the potentials, derivative potential terms, then the scalar field is almost frozen with the slow roll conditions, and this slow roll condition is when the Hubble prediction term is similar with the scalar field mass. And here is also another derivations for the equation of the motion. We will to make the combine the impulsion condition and the scalar field dynamics. In the first Bradman equations and the second Bradman equations, we can insert the anode density and the projects as in terms of the scalar field. So that here is a anode density in terms of the scalar field, and there's one more time derivations. And also for the second equation, we can insert the law and the pressure P. And if we combine the two equations, we can obtain the equation of the motion again. And why do we derive so one more times? Because we choose to calculate the epsilon and eta, the condition for the impulations, and such epsilon and eta can be expressed in terms of the scalar field. So the Hubble dot becomes the epsilon's yield at this one. I just insert this result. So the small epsilon means that the slow roll of the pi dot. And if we calculate the epsilon dot to calculate eta, and here are some evaluation process. And this is at the epsilon minus delta should be the smaller than the 1. Here's some issues. So the epsilon is already smaller than the 1, and to make the small attest, the delta should be smaller than the 1. So delta is defined as a change of the pi dot, so the acceleration of the pi. So the point was the epsilon and eta should be the small, and in the scalar field dynamics, the scalar field value should be the slower behaviors, and also the acceleration sort of the pi is also small to make the smaller atoms. And also we can parameterize and the epsilon and attach two parameters as in terms of the given potential V. The pi dust is similar to the V prime in the slow lower varying conditions, and we insist one more times the Bonus spread modifications and the pi dot are small here, so the pi dot terms negligible in small is in here. So the epsilons are given by the in terms of the potential, and for the atoms also we can insert the one more equation of the motion with additional time derivations, and also the atoms are given by the in terms of the function of the potential. Finally, sir, I would want to talk about the amounts of impulsion. Already I said the impulsion requires the 60 e-board conditions. So here's the redefines. Here is the some definitions of N again. N is HDT, and if we using the changes of the variable, the n's can be expressed by in terms of the epsilon. So the total n should be larger than the 60 as a 60 fold condition, and we know that the epsilons are given by this term. We use the potential term here. So the epsilon can be expressed by the function of the scalar field here, and the epsilon should be the small, so the build value pi should be the larger than the Planck masculine in here. And if we calculate these conditions, 6 e-fold impulsions, then we can obtain the total e-fold number in terms of the scalar field values at the rating and the scalar field values when the impulsion start. So thus we discussed the impulsion conditions with the two parameters epsilon as alpha to make the slow burning through the Hubble. Also for the such maintaining sort of the epsilon in the long time.